one little fun fact about me, I like to program, but I also like to cook. But my conditions when I cook are, it has to be done in 30 minutes and it has to be trivially parallelizable so I can make more than one thing at a time. So hopefully you got to see some of the other console talks, but if you're not, it's super high-level introduction to console. So it is a distributed system that provides service discovery, health checks, and a strongly consistent key value store. Typically, you deploy a console cluster consists of clients as well as servers. Usually, you have anywhere from 3 to 5 servers in a data center, and the number of clients can scale to tens of thousands. And then they participate in gossip. Servers also participate in a gossip pool across a WAN to other data centers as well. Console works because it's backed by two protocols that come from distributed systems research. One of them is the SWIM protocol, which you might have heard our colleague John Curry talk about. And then the other one is the RAFT protocol, which is what we use for leader election and so on. So enough about console. Let's talk about tacos. After all, we're in Austin, right? Like it's the breakfast taco capital of the world. So for the rest of my presentation, I want to talk to you about infrastructure problems that you can solve with console. But we're going to look at it through the lens of this totally fictitious startup that I've created right now called Taco Hub. What is Taco Hub? No, it's not version control for tacos. Taco Hub is a marketplace for tacos where people seeking tacos and people who want to buy, who provide tacos can come together. We're going to have locally sourced ingredients. We'll have ratings and reviews so you can go find the best rated taco in any city that you're in. You can search by obscure dietary preferences. So show of hands, who in the audience has heard of Engine 2? I'm in Austin and I saw this in a few menus in downtown Austin and I have no idea what it is. So then I looked it up and it turns out that some fireman made it. So in Taco Hub, you can search by the Engine 2 diet if you want to. And we'll also have a social network. This will be our plan to profitability. Step 1, we're going to line up our taco suppliers and build a website. Step 2, we don't know what it is yet. And step 3 will be profit. So let's zoom into the building website part. So we start with a very straightforward, familiar-looking architecture. We build a front-end web app for our taco site. We put a load balancer in front of it. And then we've come up with 2 services that are essential. One is a service for ordering tacos, and the other one is for reviewing them. And they both talk to TacoDB. I won't make any comments on whether TacoDB is web scale or not. Zooming into the taco order service itself, we know that we can't just run one instance of it. We have to have more than one instance, both to handle all the traffic that we're going to get, as well as for handling failover when one of them is down due to a memory issue or CPU issue or what have you. So the first problem we need to address is load balancing. We need to make sure that requests are balanced across all of our instances. The second issue is health checks. We need to make sure that we don't route traffic to unhealthy instances. So one common way that people do handle this is by putting a load balancer in front of their internal services. So keep in mind that we already have a load balancer to get traffic to our web app instances. And so this is, if we want to find the healthiest taco order service or we want to route requests to other instances of taco order service, we might want to use a load balancer there. But there are problems with this approach. With a load balancer, it's like one other piece of infrastructure that you need to run and maintain. The load in the load balancer grows with the number of services and the number of service instances that you have. It's still a single point of failure, and most importantly, it requires health probing. I'll explain what I mean by requiring health probing. So for a load balancer to do its job, it needs to figure out which is a healthy instance of order service. So in order to do that, typically it pings a health check endpoint or some endpoint that you configure the load balancer with. So it asks the question, is the order service healthy? And then the order service replies yes with a 200 response, yay. And this works out okay when you have a small number of services. But as things grow, so the same load balancer has to maintain or keep track of all instances of order service and all instances of review service and so on and so forth. Instead, if we use console to solve this problem, we could use console to solve this problem. With console, you can register services, giving it its IP port as well as any health checks you want associated with that service, both via config file or via the HTTP endpoint that we have. You can discover services via DNS or by HTTP. And if you use the DNS interface, the results are shuffled, so you sort of get a very naive load balancer as well. So let's look at an example of how we would register this order service with console. So we just curl our service registration endpoint with a payload, and in the payload we specify the name of the service, the port it's running in, and any checks that we want associated with that service. In this particular example, we're just exposing a /health endpoint, and we're telling console to check it every 10 seconds. Once we do this, with console's DNS interface, you can just use a query like dig to be able to look up the hostname orders.service.console, and it'll return back healthy instances of order service. One thing that I've not shown here is that by default console, when you set up console, you're going to run DNS in a different port, like 8601 or something like that. So you have to do some additional configuration either with DNS mask or something else to delegate the .console domain to forward request to the console DNS port. And that's what makes this piece of magic work, so that you don't have to specify a port number when you're doing dig. So what have we done so far? So by using console to register our order service, we've got basically zero-touch integration with any existing software. So anybody that needs to find the order service can just use orders.service or console to find it. And we don't need the load balancer, because every time you do a DNS lookup, you get a different IP. The reason we're able to do this is because of the really sophisticated failure detection mechanism that's inside console. It makes sure that the state of the world is as fresh as possible. We automatically pull failed instances out of service, and it also, when any new order service joins the network, it's immediately put into service as well. And the magic of the failure detection happens because of the SWIM protocol that I mentioned earlier, scalable, weakly inconsistent infection style processes. The surf library that's in HashiCorp surf library implements the surf protocol, and we've also made recent changes to it to reduce false positive rates. The core thing to take away here is that the network load is constant, because your load balancer is not constantly polling each service for whether or not it's healthy at a constant interval. Instead, changes are propagated into the network. So only the local agent is the one that's going to poll your service for whether it's healthy or not. And when it detects a change, then it informs the rest of the network that this particular service is failing. And then after that, that service is taken out of rotation. And this is what leads to fast propagation and convergence as well. So this is what our architecture looks like with no backend load balancer. So our web app is just making a query to orders.service.console. And because we've got console running on every node in our infrastructure, that's going to automatically send that to return back an IP that belongs to any one of those nodes that are running order service, and that request is processed. However, we still have that load balancer in the front end. And so meanwhile, at TacoDB, at Taco Hub, we've been making progress. We've been improving our site and adding more features. This is what our current state looks like. So our web app has really turned into an everything web app. Show of hands if you have an everything web app in your company, where like suddenly it's responsible for everything under the sun. I see at least a few hands. So an everything web app in my definition is something that starts out really small and is doing only one thing, but pretty soon it becomes a monstrosity of responsibilities. So in our case, we started out just doing orders, but now we're doing reviews. We have a recommendation engine, so there's a /rec endpoint, and then we also have a way to search for tacos. So now we have a search service and a search endpoint, and we want to make a small change to the review part of the site, but now we have to like deploy this huge monolith. Instead, this is where we want to go. This is our desired architecture. Instead of having the same web app do everything, we maybe want to split out these endpoints into their own web apps. So maybe orders could be processed by the /orders endpoint and go to the order web app, and we have a separate team that's responsible for that, and so on and so forth. That way we can scale these small web apps independently, and we can deploy them independently, and so on. So we can do all this with a front-end load balancer, but the problem is that when you have dynamic infrastructure where you're trying to pull out these web apps and they're going to deploy at different times, and they may shut down and restart at any time, you have to manage the configuration file for that load balancer, and you have to do it in a way that causes zero downtime. Now recently, Yelp wrote a blog post about how they were able to get HAProxy to do to get to zero downtime hot reloads of a config file. And if you read that post, you'll see that it's not a trivial problem. For example, I think they had to do something with even changing the way the TCP handshake works with the SYN packet and so on, or with the SYN response and so on. So it's definitely not a trivial problem, and it's another piece of infrastructure to manage. Instead, as an alternative, we could use Fabio for this. What is Fabio? So Fabio is actually written by our colleague Frank, who's not here today, but he works in the console team out of Amsterdam. But he wrote this when he was still when he was still working for eBay. It's a modern zero configuration HTTP load balancer. It also offers HTTPS support. It can act as a TCP proxy. The main thing, the core advantage with Fabio is that you get first-class integration with console. So let me explain what that is. So basically, the core concept in Fabio is that when you're writing a web app, you already know what endpoints that web app is serving because you're writing handlers for all those endpoints, right? Like /orders or /reviews and so on. So with a very simple change in how this app is registering itself with console, you can tell it, you can give Fabio enough information for it to construct a routing table. So in this example, we're registering the order web app with console. We're saying that it runs in port 8000, and we're adding this special tag that starts with a reserved keyword called URL prefix, and then the suffix of that tag is tacohub.com/orders. So we're basically telling Fabio that any request to tacohub.com/orders could be serviced by any of the instances that of order web app in our infrastructure. This is the architecture diagram of how requests would flow with Fabio. The dotted lines show requests flowing through, and then the solid lines show service registration. So our three order web apps, whenever they come up, they're going to register themselves into console. It doesn't matter whether you're running these order web apps in containers or through an orchestration system or you're manually deploying them. What matters is when they register, when they come up, they're going to put that special tag saying that they serve the /orders endpoint, and that's enough information for Fabio. So Fabio works with console to know that any request for tacohub.com/orders should go to one of these three instances. And it doesn't really change with a different service. So this is the same thing, but with review service. And so as we keep pulling out new endpoints from our everything web app and pushing them into their own, their separate microservices, we can just use Fabio to handle all this dynamic routing and not have to worry about messing with load balancer config files. So the core, to reiterate my point, the core advantage of using Fabio as your load balancer is that it's leveraging console to do the health check. So it's getting the same benefits as the push-based failure detection mechanism that console has. So only changes are notified back. So Fabio doesn't have to keep polling each health check endpoint all the time, causing lots of network traffic. There's no config files to manage because it's just using information that's in console already. And you've eliminated another complex piece of infrastructure. There's a lot more features to Fabio. It's used by a lot of, at least a few different Amsterdam e-commerce companies, and there's more information on the Fabio wiki page if you're curious to learn more. So let me recap the problems that we've addressed so far in Taco Hub. So We've used console to do load balancing across service instances. We were able to get massively scalable health checks because we used a push model, and we don't have to maintain any config files. So it's time for our first investor meeting. And other places, they use clicks or revenue. At Taco Hub, we use tacos consumed as our business metric, and it's looking good. It's going up and to the right. But this means that we have more infrastructure problems that we need to address. So it has come to our attention that the review service that we built is using Redis as a caching mechanism. And right now, we're running Redis on one host called Taco 1, and that's it. Like, we don't have any redundancy. So what's going to happen if Redis, if Taco 1 goes down? So ideally, what we want is to have another Redis that's kind of available on standby. It doesn't need to run all the time, but it needs to take over when Taco 1 is unavailable. The solution to this is console logs or sessions. So console logs let you do client-side leader election, and it also helps you implement semaphores. Semaphores are a more general mechanism. So with semaphores, you can say, give a specific number and say you want 3 instances of Redis instead of just 1 at any given time. And you can use either the HTTP API or the console log command to obtain a log. So let's look at an example of how to use console logs. So this is our Taco 1 host, and here I'm running the command saying console log, and I'm asking it to grab a log named with the name service Redis log. And then in the end, I'm providing a command which is run after it successfully grabs the log. So I'm saying start the Redis server after you obtain the service Redis log. So in Taco 1, because no other Redis instances are running and no one else holds the lock, Taco 1 is able to grab this lock and it starts Redis. Now, this is the same command running on Taco 2, and here it just hangs because it's waiting to acquire a lock because Taco 1 has the lock. Now, let's walk through our failure scenario here. So at this point, as you can see in this diagram, Taco 1 has holds the lock service Redis lock. Now let's say Taco 1 dies. This is one of the conditions in which console's locking mechanism or sessions implementation will recognize that this lock, the person holding this lock is dead, and so it'll release or relinquish that lock and make it available for anyone else to want to grab it. So at this point, the command that we have on Taco 2 that's trying to start Redis will succeed and it'll start Redis. And so now Taco 2 has the lock, and review service can start sending its Redis request to Taco 2 instead. So behind all this complexity, we've actually, if you're interested in more of the implementation details of how console logs or sessions work, it's heavily inspired by the Chubby paper. Chubby is Google's distributed log service. So with this locking mechanism we have in place, our caching layer, so our review service says caching layer has an active passive architecture, so we don't have to worry about what happens if that machine on which Redis is running dies, because the other one will start, and we didn't have to maintain configs or restart servers to make this happen. So one of our developers in our company has started prototyping something with AWS. Or some other cloud provider, and they really don't want to run and maintain an in-house database, and they want to switch to a cloud provider. So that's all fine and dandy, but what happens in your local dev environments, right? So you might have code like this sprinkled all over your code base because you don't really want to rack up your cloud provider bills. So in your dev environment, you maybe want to run MySQL or some other database in Docker, and you want to point your code at it. And then if it's production, you want to use the RDS or something else. So people typically solve this in 2 different ways. They either have code like this, or they use a config file. But with console, you could have the same CNAME, like talkerdb.service.console, resolved to 2 different things depending on the environment. And the way you do this is by registering this database as an external service. So what do I mean by that external service? So this is what the service registration would look like in an internal, or in dev, where you provide a port where this particular TacoDB service is running. But in production, you can give it an address that's actually a CNAME. So this is just a made-up example. But there's one caveat with this. So if you use an external service, then your console must be configured with a recursor, because console DNS only knows how to resolve everything that it knows about. So if you give it an external CNAME, then if you give it a recursor, this is just Google's public DNS, it'll be able to use that to resolve that specific Amazon RDS instance into an actual IP. But the core advantage that we get with this is that the same, basically you can get rid of all those if statements or config files in your code base, and you can just use tacodb.service.console everywhere, and it should just do the right thing in the right environment. So we've been making more progress over here in our at Taco Hub, and we've started to hire more engineers because we've started to make some money, and so we want to invest more and make our product better. But now that we have all these engineers, we have a few different, I'm calling risky features or experimental features going on in the company. So one of our engineers wants to do a large refactoring of our code base and break it up into smaller pieces so it's easier to maintain. Another engineer wants to switch out the storage layer and use a faster system. Another engineer is working on switching out our payment provider. So we use a third-party payment provider, and we're having some issues with them, so we want to switch to a different third-party provider. So all of these I would call are high-risk features with a high payoff. So if it works out, it's great. But if it doesn't work, we end up breaking our site and stopping people from getting to their favorite tacos. So what we want to do is have a safe way to roll out these features. And there are existing solutions to this. So you can use an A/B testing framework. There are a few ones available open source, as well as companies that provide A/B testing as a service. So I would say that they're probably a reasonable solution, but one thing to remember is for the most part, A/B testing frameworks tend to split on user characteristics rather than on machine or host characteristics. You can kind of modify them to make it work, but it's a little more difficult. And there's a lot of overhead for something simple like just a feature toggle, like enable this in a selective way. So one pattern you can use is leverage, if you already have console deployed everywhere in your infrastructure, you can leverage it to build very simple feature toggles. So in our example, we're going to write a flag value to console where the flag value is suffixed by the host name or node name in which we want that feature to be enabled in. So in this example, I'm saying console kv put new payment API taco1 true. So I'm saying that I only want to use the new payment API in the taco1 in a node named taco1 and nowhere else. And then on the application side, so in our ordering service, when we get the new payment API, we're going to ask console for new payment API / host name. We already know our host name or node name. So if it's true, then we're going to use the new payment API, and if not, we use the old one. That's it. That's all is required to have a very simple feature flag built using console. So in terms of how we would actually roll it out in practice is, we first set a key called new payment API taco1, and then we watch the logs for taco1, we watch our dashboards, we make sure that no alarms go off, everything's working fine, we're still making money, the new payment API is working correctly, and so on. And then after that, we do the same thing, but we set it for taco2, and then we do the same thing, we do the same thing and we set it for taco3, and that's how we basically rolled out a feature, starting with one server and gradually rolled it out to all the other servers in our infrastructure. So there are some advantages to taking this approach. Beyond just feature toggling, it enables doing dark mode features. So what I'm defining as dark mode features is, say you're working on something that takes a long time to roll out, but you want to release small parts of it every week so that you're not making your teammates cry with a huge commit with 300 files changed or something like that. So you might want to break it up into small parts and still release it slowly, but turn it off. So you put all that behind a console kv feature flag. So all that code is there, but it's not actually enabled. And then when you're finally ready to enable, then you turn the dark mode into a light mode by setting a feature flag. Another really nice advantage of putting things behind feature flags with console is it allows you to easily disable something without needing a code deploy. So in spite of our best efforts, we watch logs, something is okay, but like maybe at the midnight boundary, something goes wrong with our payment API and we need to roll back. It might take much longer to roll back the code, but if we just set that key to false back in console, it's instantly disabled for everyone. So this is a nice technique to keep in mind for doing experimental features. So our site has our company has all these developers, and something that developers really care about is developer velocity with being able to deploy code to production quickly and fast. So I want to show you how to leverage consul-template to build a very bare bones. I'm not going to call this a sophisticated solution. It's a bare bones but a functional continuous deployment solution. So what is consul-template? If you haven't heard of consul-template, it's a standalone tool that integrates with console only for reads. You can't do writes with it, but you can retrieve keys and services from console and render them into a template. It's built on top of the Golang's templating language, and it's very easy to use. So there are 3 parts to using consul-template, and the last part is optional. So you run consul-template like this, and you can have more than one of these. In this example, I just have one. So you specify an input template, you specify an output file, and then the third part, like you specify an optional command that you want to run once the template has successfully populated the output file. So this is kind of the flow of how things would work with consul-template. Consul-template will issue a blocking query to console to watch for changes for whatever key you're asking it to watch. And then when it hears back from console, it's going to populate the file with the value for that key. So in this example, we're going to make Taco Hub get a very bare bones continuous deployment system by giving it our input template file, and we're going to have it populate a file called reviewservicelatest.txt. And then when it's successful, we're going to have it run the deploy.sh script. So you can have your continuous integration system, so the thing that makes sure that all your builds are green and so on. When it's finished successfully, you can have it we're going to have it write the SHA hash of the code that we want to deploy to a path in console called review_service/latest. Then this console template is going to watch that key space, and when it changes, we're going to write that SHA hash to the file, and then that deploy script basically just reads the file and then knows where to download the code corresponding to that specific version, and then actually execute a deploy and so on. So sorry, this is just saying what I described. So we perform a blocking query, we store the value in the file, and we run the script after the update. And with this, we have a very bare bones functional continuous deployment system using consul-template. There are more use cases for consul-template as well. Sometimes you might not want to have console in the critical path for whatever reasons. So if you want to kind of have a bridge where consul-template is the one that's watching console, so that way if console goes down, you're not taking down anything else that's reading from it directly. So one use case, for example, is say you have an application that requires a pool of database servers. You can have consul-template be responsible for populating a config file with the IP addresses of those database servers, and then have your application read from that file instead. Another common use case is to generate application config files from the KV store. Again, like if you're in a large enterprise and you're trying to get, you've installed console everywhere and you're trying to get people to move to it, it's hard to make every application change its behavior to read its config directly from the KV store. Instead, you can use consul-template to kind of paper over that by producing the config file that the application already knows how to load and understand. So here are some ways in which you could use it. So it's time for another investor update. So our investors are really impressed with our growth, but now they've given us more responsibility. They want us to expand internationally and provide tacos around the world. But this translates to us having data centers around the world. And that also means that we need to think about availability around the world. What does our availability story look like? The basic thing that we start doing with this let's just take 2 data centers as an example, is we need to run our stack in both data centers. So we have our front end and our order service, review service, and our TacoDB, and they're both in both data centers. Zooming in on just the review web app and the review service, let's just say that on the left is the US data center, and on the right is the Europe data center. What happens if the reviews of all instances of the review service in the US all go down at the same time because of machine issues or code bugs or what have you? So at this point, what we want to have happen is requests to review web app that need the review service should just automatically fail over to the review service that's running in Europe. And how do we do that? So there are ways to do this, like you could have a manual override. Because we're already using DNS, we could modify our DNS records or something to kind of force order service to use like a CNAME like order service EU console, which resolves to like a IP address of a order service that's in the other data center. The problem is this is not really transparent to the application. It requires at least some amount of downtime or somebody noticing and doing this work. And in some cases, it may even need an application restarts for the app to notice that its config has changed. So the solution that I'm proposing to this is console prepared queries. My colleague James also talked about prepared queries in his talk yesterday. It's not a very super well-known mechanism, so I want to dive a little bit more deeper into it, like what it is and what problem it solves. So prepared queries are centrally managed policies that allow dynamic behavior for service lookups without having any custom knowledge from applications. So using prepared queries, you can define which service to look up, what order to look up in, and rules for what to do when anything is not available when a particular service is not available in the local data center. And prepared queries can integrate with the DNS API, but you can also use the HTTP API to execute them. So this is an example of a prepared query for solving the problem that I talked about. Like what I want to do is when the review service is down in US, I want to use the EU data center as the backup. So in order to do that, I first need to use the V1 query endpoint to create a prepared query. In this specific example, I'm using a prepared query template. So a prepared query template kind of simplifies your workflow because you don't have to create, if you have a dozen services in your infrastructure, you don't have to create a prepared query for each service. Instead, you can use this name prefix match, which is like a catch-all template, and it's going to match any service. So you're saying for any service in my infrastructure, assuming that you're running the same stack, identical stack in all data centers, you're saying that for any service in my infrastructure, if it fails over, this is the order in which I want to resolve it. If the US data center fails over, then I want to use EU as the backup. There's only one change that we need to make on the application side in order for this particular geo failover or transparent failover to work. So remember when I said earlier that when the review web app or order web app wants to talk to a service, they just say reviews.service.console or orders.service.console. Instead, the config file needs to say reviews.query.console. That's the only thing. That's it. Once you do that, it should automatically do the right thing and fail you over when all instances of review service in the US are down. So what happens once you make that one change, when review service is down, all traffic for review web app is going to talk to review service in Europe. However, for this to work, a lot of things are coming together in console to make this work. So the first thing is our robust failure detector that's inside console observes that all nodes in US, all nodes of review service are down. Then the second thing that happens is the DNS interface inside console knows how to interpret reviews.query.console and it interprets the codified behavior that we gave. So the codified behavior that we set up was to fail over to EU. So now it sends across DC request to EU for review service, and it returns IP addresses of review service in EU. And the review web app had no knowledge, didn't need to know any of this. So as far as the review web app is concerned, it's just making a DNS request and getting back IP addresses and sending requests to them. That's it. So in a nutshell, like if I had to tell you one thing about prepared queries, like what's your core takeaway, is that it helps you automate failover behavior. So I want to recap all the different things that I talked about today. So we saw how to use Consul for service discovery and how it scales health checks, and how we can use the DNS interface for a very simple load balancer. We saw how you can use Fabio and Consul together when you're trying to pull out lots of small HTTP microservices out of a single monolith and to load balance across them without needing to mess with load balancer config files. We saw how to use console logs to do active passive instances so that you don't have a single point of failure. We saw how to use console KV to do feature toggles. We built a very simple continuous deployment system with consul-template. And then finally, we saw how to use prepared queries to do transparent data center failover. So in a nutshell, Consul is really a Swiss Army knife of solutions to your infrastructure problems. I'm not here to tell you that you need to use all of these things or you have all these problems, but hopefully you saw at least something in this presentation that you could go back and apply in your environment. And I hope this was useful. Thank you.